Good morning students, I hope you all are good. Today we are going to discuss lesson 3, magnetism and magnetic effect of electric current. In this lesson we have discussed a number of topics, isn't it? Today we are going to discuss a new topic, force on a current carrying conductor placed in a magnetic field. What is our topic? Force on a current carrying conductor placed in a magnetic field. This is very important 5 mark questions. Maximum number of times this question asked in the public examination. So very important question. This question is based on in our previous chapter, second lesson, current electricity. We are discussed drift velocity, relation between drift velocity and current. No, that question, that equation we are take, we are complete the question. So force on a current carrying conductor placed in a magnetic field. Okay, so when a current carrying conductor placed in a magnetic field, first sentence, if you take one current carrying conductor, that current carrying conductor placed in a magnetic field, see that? This is the magnetic field. Assume so now I will take one current carrying conductor. So like current carrying conductor looks like a wire. Current carrying conductor placed here, cross symbol indicating magnetic field. What is here? Magnetic field. Uniform magnetic field. That magnetic field, how that means perpendicular to the plane of the paper. How that? Uniform magnetic field, that magnetic field perpendicular to the plane of the paper. So this is the current carrying conductor. This current carrying conductor, we have to keep uniform magnetic field. So the force experienced by the conductor or wire, see here, the force experience the wire is equal to the sum of the magnetic Lorentz force of each charged carrier of the wire or conductor. So we have taken one current carrying wire or conductor placed in a uniform magnetic field. How that magnetic field means perpendicular to the plane of the paper. That's why I mentioned the cross symbol. If cross symbol means how that perpendicular to the plane of the paper. See, I suppose this is the paper. This is the paper. Okay. How that magnetic field means? See. Paper, this is paper, and the lines and the arrow mark represent what is that? Magnetic field perpendicular to the plane. In here we have to keep that, what we have to keep? One current carrying conductor. That current carrying conductor length is what is that? We are represented by L. We are represented by L. In that current carrying conductor looks like wire, or assume wire. The wire has area of cross section is A. What is this here? This is represented by area of cross section A. The wire has the area of cross section. Next, what is A here? A is the area of cross section. Area cross section of the wire. Okay. Next, what is the wire? If we consider total wire means, no, we are considering a small element on the wire. A small element on the wire. The small element represented by is dl. What is I means? I is the current entering the current through the wire. What is that? current through the wire. So we have to assume a small element on the wire. This is the small element. That small element area is A. What is small element length? The small element is dl. That means length. Here dl represented by length of the small element. Okay, got it. I. What is I means? Current flows through the wire. Current flows through the wire. So we already discussed in our previous chapter. What is our previous chapter? Current electricity. Relation between current and drift velocity. I is equal to N A E into V. Equation number 1. Here what is V? D means drift velocity. We have discussed what is drift velocity in our previous class, very detailed, isn't it? Drift velocity defined as the velocity which acquired a parent volume of the electric field, isn't it? So next, what is E means? Charge of the electron. A means area of cross section. N means number of free electrons. Here, see, assume that this is the wire. When the current flows, the wire has the free electrons. See, these are the free electrons. The direction of free electrons is opposite to the, how that means, the direction, this is the direction of free electrons. Direction of free electron opposite to the flow of current or direction of the current. So the direction of free electron is, this is the direction. This is the direction of free electron that is opposite to the direction of current. Due to the drift velocity, Vd represented by drift velocity. So drift velocity is the velocity the free electron drifted acquired per unit volume. Okay, so that is equation number 1. So how that here the free electrons move opposite to the direction of current due to the drift velocity. So the conductor where we have kept, the conductor is kept uniform magnetic field, isn't it? Am I correct? In the beginning I explained no. So the conductor placed where we have kept uniform magnetic field. So the uniform magnetic field experiences the force. That force represented by F vector equal to minus E Vd into B vector. Minus E, the charge of the electron is negative. So why this equation number 2 arrived? Because the conductor placed in a magnetic field. The magnetic field experiences the force minus E Vd. Next. N is equal to small n equal to N by V. What is that means? Number of free electrons per unit volume. So number of free electrons per unit volume of the wire. What is that? Volume of the wire. Next, what is N? N indicates number of free electrons per unit volume. No. So N is nothing but number of free electrons per unit volume. Then volume V is equal to area into small, we are considering element of the wire. Volume we have to represent. So from that equation I want to write N capital N equal to small n into V. What is V? See that here. When we substitute V, N into A into dl. So equation number, what is this equation means? Equation number 3. So N, capital N represent small n, A into dl. Everything we have to, don't memorize, everything step by step you have to understand and write that. So small n, number of free electrons per unit volume of the wire. So number of free electrons per unit volume of the calculate means area of the small element and length of the small element. Because volume is the area into length. So n is equal to, now substitute capital N. So n is equal to Na into dl. So here when the free electrons and free electrons move opposite to the direction of current, no. So df vector equal to capital N minus E Vd into B. Number of free electrons. So now this is equation number 4. Substitute equation number 3 in equation number 4. See that? So df equal to n minus e vd into b vector, equation number 4. Substitute equation number 3 into equation number 4. What will get? See, so I rub this one. There is no doubt. What is this? A conductor placed in a uniform magnetic field. How that magnetic field? Perpendicular to the plane of the paper or planar. So the force experienced by the conductor or wire is equal to the sum of the magnetic Lorentz force of each carrier of the charged wire. Okay, so we have to assume a small element of length dm, area of cross section, when current flows, it is opposite to the free electron. So gives the relation between current and drift velocity. We can write previous class we are chapter derive the equation. So drift velocity and explanation and magnetic Lorentz force. So substitute equation 3 in equation 4. We are getting df vector equal to. So what is instead of n, what we have to write? N capital A dl. Am I correct? Rest of the term minus E Vd into B. Okay. So in this equation, I want to write like that. How I want to write means, see here. I dl into B vector. What is the reason? Because IDL vector equal to NA DL, okay, VD. So IDL is nothing but NA, what is that? Minus E NA DL into VD, represented by what is that? IDL. This is the vector form. df vector equal to IDL vector into B vector, isn't it? In magnitude, what is that? F vector equal to IL into B. What is that? IL into B vector. This is also magnitude. In vector form, there is no vector form. This is vector form current, this is vector form without current. So in the differentiation, but here there is no differentiation. In magnitude, what is that magnitude? F is equal to BIL sin theta. Equation number, last equation is 4, equation number 5. Very important equation. F is equal to BIL sin theta. Use that equation. We have to derive, or we have to discuss two cases. Case 1 and case 2. First, using the equation number 5. Using equation 5. Case 1. What is that case 1? See that? This is magnetic field. Assume uniform magnetic field. So now the conductor is placed, how that? Parallel to the magnetic field. How that we have to place the conductor? The conductor, case 1, the conductor placed parallel to the magnetic field. Parallel means theta is equal to 0 degree. So what is the force? F is equal to BIL sin 0 degree. Sin 0 0. So F is 0 into anything 0. So what is the force? Force should be 0. What is that? 0. Important one mark question. When the conductor is placed parallel to the magnetic field, what is the force? 0. In case 2, just opposite that, when the conductor is placed perpendicular to the magnetic field, theta equal to 90 degree. So F is equal to BIL sin 90. Sin 91, so F is equal to BIL. That means what is the force? Means the force should be maximum. How that? The force should be maximum. So when the conductor is placed perpendicular to the magnetic field, what is that force? The force is the conductor produces, wire produces the maximum level. But conductor is placed parallel. Here what is that? Second, perpendicular to the magnetic field. What is the force? Maximum. They will ask 1 mark level question. Length of the conductor they will give, current they will give, magnetic index to find the force. Okay, so you will attend very easily. They solve the 1 mark or 2 mark level problems. Next, using this force, we have to study Fleming left hand rule. In the 10th standard itself, you studied, I hope, Fleming left hand and right hand rule. Fleming left hand rule used in the motors. Fleming right hand rule used in the generator. We will discuss Fleming right hand rule in our forthcoming lesson 4. So Fleming left hand rule. Stitch the 3 fingers in our left hand like that. Stitch the 3 fingers in our left hand and mutually perpendicular to each other. See that? This thumb, forefinger, middle finger. Thumb, forefinger. What is this called? Middle finger. Stitch the 3 fingers mutually perpendicular to each other in our left hand. Middle finger indicates direction of current. What is that? Forefinger indicates. What is that? Forefinger indicates and middle finger indicates, thumb indicates. See, forefinger indicates direction of magnetic field. And middle finger indicates direction of current. Thumb indicates direction of motion of the conductor. What is that? Motion of the conductor. And Fleming left hand is used in the motors. Electric motors. Fleming left hand is used in the electric motor. Very simple. This is very important 2 mark question. State Fleming left hand rule. Stitch the 3 fingers in our left hand mutually perpendicular to look like C. What are the first called? What are the name of the finger? Thumb, forefinger, middle. Forefinger indicates always direction of the magnetic field, and middle finger indicates direction of the current, and thumb indicates direction of the motion of the conductor. Don't change the order. First forefinger, middle. Next what is that? Thumb. So this is very important question. Force on a current carrying conductor placed in a magnetic field. 5 mark. Suppose in that 5 mark they will ask for explain and write Fleming left hand rule. You will write. Otherwise, they will give the definition of that means force is maximum. Force is 0. At what time? What is the condition? If conductor is placed parallel to the magnetic field, the force is 0. The conductor placed perpendicular to the magnetic field, what is the force? Force is maximum. If you have any doubt in this question, please ask me. It is very important question and use the formula, very simple formula to derive the questions, mathematical expression also. Okay, thank you.